So, Chapter 5, we're going to be talking about polynomials. So, polynomial, if we break the word down, poly means many, and nomials means numbers. So, when we're talking about a polynomial in standard form is going to have the general form that looks like this. So a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 all the way down to a sub 2 x squared plus a1 x plus a0. So the reason we're using all of these subscripts and we're using a sub 0 through a sub n to represent constants. So we have that a sub I is a constant. And we'll notice that on each monomial term inside our polynomial, the subscript on the a is always the same as the power on the x. So this gives us an alternate addressing system when we want to talk about the coefficients of a polynomial. So for example, if I had the polynomial f of x equals 5x cubed minus 7x squared plus 2x plus 3, and I asked, well, what is a sub 2? Well, a sub 2 would be the coefficient on the x squared. So in this case, a sub 2 would be negative 7. Similarly, if I asked what a sub 3 was, my response would be 5, because the coefficient on the third degree term is a 5. So we've seen some things like this in the past when we were using quadratics, which we'll talk about in detail in 5.3. But in that naming convention, we always used a, b, and c. This generalizes that to any polynomial, regardless of its degree. All right. So the next thing we want to talk about is called the leading term test. So if f of x is equal to a n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down, the monomial with the largest degree is called the leading term. So in terms of this, our leading term is always going to be the one with the largest degree. So our leading term would be a sub n x to the n. We then have a couple of different possibilities, and that's where this picture comes in. So our first thing that we need to check is n is even. That means we're going to go up, or n is odd. So in terms of our leading term, the first thing we're going to look at is the n value. If it's even, we're going to take this branch. If it's odd, we're going to take this branch. The next thing we need to look at is the coefficient a sub n. And then we have two possibilities. If a sub n is positive or a sub n is negative, then we're going to have the same two possibilities down here. A sub n is positive or a sub n is negative. So if n is even and a sub n is positive, the end behavior of our graph is going to be like this. If n is even and a sub n is negative, the end behavior of our graph is going to be this. So if a sub n is positive, our graph starts up and it ends up. If a sub n is negative and n is even, our graph starts down and ends down. In the cases where n is odd and a sub n is positive, our graph is going to start down and end up. And if n is odd and a sub n is negative, our graph is going to start up and end down. So for polynomials, there is exactly 4 possibilities for our end behavior, and these 4 pictures are it. It can start up and end up, it can start down and end down, it can start down and end up, or it can start up and end down. And these are our 4 cases, and they depend on n and a sub n. Let's take a look at our first example. We wish to sketch the end behavior of f of x equals negative 5x to the 12th plus 6x to the 8th plus x cubed minus pi to the 20th power. So to use the leading term test, the first thing we need to identify is the leading term. So the leading term is the monomial with the largest exponent. That's going to be negative 5x to the 12th. So note, this is not the leading term. Even though it has an exponent of 20. Why is that the case? Well, when we're talking about the degree of a monomial, we're always talking about the exponent on a variable. Pi is not a variable. And the degree of a constant is always 1. Or I mean, not 1 is always 0. Sorry, I misspoke. It's degree 0. So our leading term then is negative 5x to the 12th. So we're going to identify our n and our a sub n. So our n is going to be 12, and our a sub n is going to be negative 5. So for each of these, for n, we have to check if it's even or odd, and if for a sub n, we have to check if it's positive or negative. So if n is equal to 12, 12 is even, so n is even, and a sub n is negative 5, so that means a sub n is less than 0. So we're going to be using even and negative, so even and less than 0. So we come up to our chart. For even, we're going to go up, and for less than 0, we're going to go down. So that brings us to the following diagram. So that tells us that our graph starts down and it ends down. So the end behavior of our graph is going to be it starts down and it ends down. So it's worth noting this part right here. The leading term test tells us nothing about what happens in the middle. So the reason I choose to put those squiggles is that's my way of representing that this test doesn't tell me anything about what's happening in the middle. All it says is that the graph starts down at negative infinity, and at the very end it's going to go back down to negative infinity. That's it. The leading term test gives us no information about what happens in the middle. We'll have to use some other tools to help us figure that out. All right, so to resolve our U-try, first thing we need to do is identify our leading term. So our leading term is going to be 3x to the 7th. So that's our a sub n and our x to the n. So our a sub n is going to be 3, and our x, or our n rather, is going to be 7. So n equals 7, that tells us n is going to be odd, and a sub n is 3, so a sub n is greater than 0. So we go look at our chart. If n is odd, we're going to go down, and if a sub n is positive, that means we're going to go up. So the end behavior of our graph is going to be it starts down and it ends up. So then based on what we have, we're going to start down. We don't know what happens in the middle, and it's going to end up. All right, the next thing we want to talk about is the multiplicity of a 0. So we need a definition. So let's remind ourselves first, what is a 0? So a 0 is an input C such that the output f of c is equal to 0. So remember, as an ordered pair, this is the point c comma f of c, but f of c is 0. So it's actually the ordered pair c comma 0, which is the x-intercept. And we talked about this before, so let's recall that zeros, solutions, and x-intercepts are the same thing. So that's just a reminder of our definition of what it means to be a 0. So a 0 is an input that when we put it into the function, 0 comes out. On a graph, it's the same as the x-intercept. In terms of an equation, it would be the solution to said equation. But now we want to talk about another modifier for zeros, which is their multiplicity. So if f of x is factored, so it looks like this, f of x is equal to x minus a to the n1 times x minus b to the n2 all the way out to some other thing, x minus some other number, we'll call it ml raised to the n sub l. something like this, the multiplicity of each 0, so the multiplicity of the 0 A is n1. So we'll notice the 0A is if I plug A into this term right here, A take away A is 0, which would make that entire polynomial equal to 0 because it's factored. Because 0 times anything is 0. So the multiplicity is going to be the exponent on the linear factor. So for our next factor, the multiplicity of B is n2, and so forth. So if we were to look at the following polynomial, the 0, x is -5, has multiplicity 3. The 0, x equals 7, has multiplicity 10. So the 0 of each one, x equals -5, is the 0 of this factor. Because if I replace x with -5, -5 plus 5 is 0. And 0 times anything will give me 0. So that is a 0. And the factor is repeated 3 times. So it has multiplicity 3. Similarly, if I look at the 0, 7, 7 take away 7 is 0 here. But that factor is repeated 10 times. So the 0, 7 has multiplicity 10 in this example. The multiplicity of a 0 changes the shape of the graph. There are 2 possibilities at a 0. So if the multiplicity of a 0 is even, the graph is tangent to the x-axis at the 0. So instead of tangent, I prefer the word bounces, and we'll see why. So in terms of a picture, what this means is that if we have a graph and it has an even multiplicity, the graph is going to come down, touch the x-axis, and turn around. So technically it is tangent at that point, which means it's going to be parallel to the x-axis as it turns around, but I prefer the descriptor bounces. It comes down, hits the x-axis and bounces back up, or it comes up and hits the x-axis and bounces back down. So when we're even, we're going to have this type of behavior. If the multiplicity of a 0 is odd, the graph crosses the x-axis at the 0. So in terms of our picture, if we had our 0, the graph is just going to cross at that point if the 0 has odd multiplicity. So zeros with even multiplicity bounce. Zeros with odd multiplicity just cross the axis at that point. And those are the only two possibilities. And the way we determine which it is if the degree is even or the degree is odd. All right. So let's go ahead and use those definitions to do example number 2. So find the zeros, or x-intercepts, of f of x equals x to the 5th minus 3x to the 4th plus 3x cubed minus x squared, and give the multiplicity of each 0. So we need to factor this polynomial. So we look at our polynomial here, and the first thing we notice is that we have a GCF. So our greatest common factor is going to be x squared. So if I factor out an x squared from x to the 5th, that's going to leave x cubed minus 3x squared plus 3x take away 1. So we still need to factor this cubic polynomial. So we're going to factor by grouping. But we have to be careful with the way we're going to group. So we're actually going to group the first term and the last term together. So that's going to give us x squared times, and then group 1 is going to be x cubed take away 1, and group 2 is going to be the two terms in the middle. So minus 3x squared plus 3x. So this is our group 1. And blue is going to be group 2. So we need to factor each of these. So group 1 is one of our special forms. It is the difference of cubes. And just to remind us, the difference of cubes formula is if I have x cubed minus a cubed, this factors into x minus a times x squared plus ax plus a squared. So our first group, our a is 1, and our formula, so we're going to get x minus 1 times x squared plus x plus 1. And in our second group, we just have a GCF, and since our leading term is negative, we will factor out a negative 3x. So in group 2, we factor out a negative 3x, and that leaves behind an x take away 1. We then have a common binomial factor. So we're going to factor out our x minus 1. So then my x squared comes down. I factor out my x minus 1, which is my common binomial factor, and that's going to leave behind the x squared plus x plus 1, And in the second term, it leaves behind a negative 3x. And we have x squared times x minus 1. Collecting our like terms, we have x squared minus 2x plus 1. And then we need to factor this quadratic. We need factors of 1 that add up to negative 2. So this factors into x minus 1 times x minus 1. So finally, collecting all of our like factors, we are going to have x squared times x minus 1 cubed. So we have two zeros. So the 0 of x squared is x equals 0. And the 0 of x minus 1 is x equals 1. The 0, x equals 0, has multiplicity 2. And that comes from the exponent. And the 0, x equals 1, has multiplicity 3. So then what does that tell us? Well, based on what we just talked about in the previous examples, if our multiplicity is even, the graph is going to bounce off that 0. And if the multiplicity is odd, it's going to pass through. So the graph bounces at x equals 0 and will pass through at x equals 1. So let's draw a picture with our calculator of this graph. So if we go y equals, and we go x to the 5th minus 3x to the 4th plus 3x cubed minus x squared, and we go graph, let's zoom in a bit. So we go zoom, let's go in. Zoom in just a little bit more. Go negative 0.5. We'll make our x, well, not negative 5, so negative 0.5. Let's make our x max 1.5. And let's change our x scale to 0.1s. And let's just go from negative 1 to 1 in our y values, and we'll go 0.1. And you can just barely see it come down, and then it crosses back over at our points. So we see it goes up here, it bounces, comes back down, and then finally at 1 it goes back up above the x-axis. Because if we go way back out, if we go back to our zoom standard, we'll see that for a 5th degree polynomial, we know it should start down and end up, which it does. Then the bouncing part tells us how the graph behaves in the middle, where it bounces off 0 and passes through 1. And that's how we get starts down, ends up, and a pretty basic shape that matches what we get. So combining the two things we just talked about, without a graphing device, we can know the behavior of a polynomial. All right, the next thing we need to talk about is what is called the intermediate value theorem. The intermediate value theorem states if f of x is a continuous function and f of a is less than 0, which is less than f of b, then there exists a number c such that, in between a and b, such that a is less than c is less than b, and f of c is equal to 0. So what this theorem is saying in a picture, if we have two inputs, a and b, and f is a continuous function, and we know that if we go down to our point, a, f of a, and we go here to b, f of b, so notice here we have f of a is less than 0 because it's below the x-axis, so f of a is less than 0, and f of b is bigger than 0 because it's above the x-axis, then the following must be true. It says that somewhere in between a and b, there exists some number c, where the ordered pair of that point is c comma 0. So it's telling us there's an x-intercept there. Well, that 0 has to be equal to f of c. So basically, what the intermediate value theorem is saying is that if our graph changes sign, if it goes from positive to negative, it's also true if it does it the other way, then somewhere in between those inputs, there has to exist a 0. And if you draw this picture, since f is continuous, it's not allowed to jump over the x-axis. It has to cross, right? Because if it goes from a positive value to a negative value or a negative value to a positive value, somewhere to change from positive to negative, you have to cross the number 0. So it's worth noting that this can also happen in the other direction. So f of b is less than 0 is less than f of a. So this is really an or statement for these two things. So as long as it changes sign, then there exists a number in between, like we see in this picture, where it must equal to 0. So we want to use the intermediate value theorem to show that f of x equals x to the 6th minus 6x cubed plus the square root of pi has a 0 in the interval 0, 1 and a second 0 in the interval 1, 2. All right, so to show it has a 0 in the interval 0, 1, we have to check f of 0 and f of 1. Well, f of 0 is 0 to the 6th minus 6 times 0 cubed plus the square root of pi. So that's just going to be the square root of pi. And we know that this is going to be a positive number because the square root of pi is positive. If we check f of 1, well, that's 1 squared minus 6 times 1 plus the square root of pi. 1 squared is 1. 1 times 1 cubed is 1 times negative 6 is negative 6. So 1 take away 6 is negative 5 plus the square root of pi. Well, we know the square root of pi is smaller than pi, and pi is 3.14. So negative 5 plus the square root of pi is going to be negative. You can punch it into your calculator and get a decimal approximation if you wish. So then this tells us that we have f of 1 is less than 0 and f of 0 is bigger than 0. So we have f of 0 is bigger than 0 is bigger than f of 1. So this is positive. This is negative. So by the intermediate value theorem, if I have a positive output and a negative output, somewhere in between the inputs A and B, there must be a 0. So somewhere in 0, 1, there exists a C such that f of C is equal to 0. So now, if we want to do the same thing, we want to show there's another 0 in the interval 1, 2. Well, we've already checked f of 1 in the first part. We know f of 1 is less than 0. So let's try f of 2. Well, f of 2 is 2 to the 6th minus 6 times 2 to the 6th plus the square root of pi. Not to the 6th. The second one is only to the 3rd. There we go. So let's see. 2 to the 6th is 2 times 2 is 4, 8, 16, 32, 64. So we have 64. 2 cubed is 8. 8 times 6 is negative 48 plus the square root of pi. So 64 take away 48 is going to be equal to 16 plus the square root of pi, and that is bigger than 0. So we have f of 1 is less than 0, which is less than f of 2. So in the interval 1, 2, there exists a number, I'm not going to call it C because we already used that, D, such that f of D is equal to 0. So graphically, what does that tell us? This graph has x-intercepts in between 0 and 1, and it has an x-intercept between 0 and 2. All right, so let's combine all of this. So we have f of x equals x to the 6th minus 6x cubed plus the square root of pi. So if we look at our n behavior, we have a sub n is 1 and n is 6. So this is positive and even. So positive and even says our n behavior looks like this. So our graph starts up and ends up. Okay. Then we know that somewhere between 0 and 1, it's got to cross the x-axis, and then somewhere between 0 and 2, And if we plug in 0, which we did, we got the square root of pi. So our graph starts up, comes down, between 0 and 1, it does something, it's going to turn around. And then between 1 and 2, it goes back up, and it's going to do something like this. We don't know what's going to happen. It might wiggle in here, do something like this, and then take back off up. All right, well, let's graph that on our calculator and see what we get. So we go y equals, and we have x to the 6th minus 6x cubed plus the square root of pi. We go zoom 6 to get back to our standard window. And so we see it came down. Our graph's not 100% accurate. We notice that we weren't able to figure out the wiggles, right? But we did get our x-intercepts correct, at least approximately, right? So in order to have a better idea of what this graph really looked like, what point did we need to know? Well, it would be really helpful if we could figure out this point right here, which is going to be its global minimum, right? Because we see from the picture, we did have our intercept, our graph went down, it didn't wiggle like this, it came down to a minimum, and then it shot back up as we went by. But we did get the end behavior right. Starts up, ends up, and in fact we got our x-intercepts pretty close, right? We knew where they were, at least within 1 unit. All right, so now let's look at our next one, which involves actually this exact polynomial. It says use our graphing device to estimate the real zeros of this function, the relative max and the relative min, and the range of the polynomial function. Okay. So we've already got it in our calculator. So we want to use our calculator to actually find the zeros. So we know that there are 2 zeros. We know our first 0 is in between 0 and 1, and we know our second 0 is between 0 and 2. So if we go second and trace to pull up our calculate menu, we want to find our 0. So we're going to go down and select choice number 2, and then it's going to ask us some questions. So it's going to ask us for a left bound and a right bound. Well, we actually found those when we used the intermediate value theorem. You don't have to use these ones, but you have to pick something to the left of the 0, and you have to pick something to the right of the 0. Well, x equals 0 is to the left, and then I move to the right, which is about 1. Okay, that's there. I hit enter, and then guess. Just move back till I'm closer. I hit enter, and my calculator gives me the following for my first 0. So the 0 that is in between 0 and 1 occurs when x is approximately 0.6779 and some change. We can do the same thing again. So second trace, we want to find a 0, but this time we're looking between 1 and 2. So I go over to 1, hit enter, and then I'm going to move over till my cursor is closer to 2. All right, enter, and then guess. I just move back closer, hit enter, and my calculator gives me the following. So my 0 in between 1 and 2 is about 1.7. 1.785, blah, 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 right? So to as many decimal points of accuracy as we need. So as mentioned up here, the other thing that would be very helpful to find would be our minimum. We're going to find the minimum in the same way that we were finding the zeros. In fact, it's under the same menu, so we go second, and our trace key, get our calculate menu, and we notice this time we have our minimum is choice number 3. So we go down to choice number 3, and we need something on the left and the right. Well, we know that our minimum occurs somewhere between our zeros, right? So our zeros were 0.6 and 1.7, so I go to the left to about 0.6, okay? Don't want to go above the x-axis, and then to the right, I move over here. Don't want to go up too much, there we go. And then I get a little closer, press enter, and it gives us the following value. So our minimum is located at the ordered pair 1.442, and the y value is negative 7.22. So now the very last thing we were asked is, what is the range? Well, we know the end behavior is our graph starts up and ends up, and we have a minimum at this point. So our range is going to be approximately negative 7.228, and I'm going to round it to the nearest thousandth, all the way up to positive infinity. And we get this value comes from our approximation of that minimum value. So we can use the intermediate value theorem and some other things to help us know where to look for things. We then can find approximations with our graphing calculator to help us find those actual points, or at least approximations of them. All right, so let's go ahead and put this in. So we have x to the 5th plus 5x squared minus 2. And we graph, we get something that looks like this. We're trying to find our maxes and our mins and our zeros. So I'm going to change my window up a little bit. I'm going to change my x min to negative 3, my x max to positive 3, and do the same thing with my y min and my y max. So when I do that, I get the same picture, but now it's going to be a little easier to work with because I'm zoomed in on all of the important parts. So when I look at my graph, I now see I have a max and a min, so it has both, and I have 3 zeros. So let's find our zeros from left to right. So let's find our smallest zero. So we go second, calculate, and go 0. We're going to have to move our cursor for a while till we're to the left of the smallest 0. Okay, so I'm finally to the left. I press enter. Then I move to the right, press enter, and then guess. And I get my first 0 is located at negative 1.6. All right, so let's find the middle 0. So I'm going to rinse and repeat that same process. So I go second and trace, choose choice number 2 for 0. And now I'm going to move a little closer to my second 0. So I'm still to the left of it. I press enter. Then I move to the right of it. Press enter. Move a little closer for my guess. Press enter. And my second 0 looks like it is at about negative 0.65. And then we have our last 0, or the positive one. So second trace again. I go to 0. I'm going to move over a bit, get closer to it. And to the right, and I move back, guess, and I get the following. So those are our 3 zeros. And then to find the maxes and the mins, we're going to do a very, very similar process. So we're going to go back into our same menu. So second, calculate. Let's find our minimum first. So I need to move to the left of my minimum. Okay, so I'm to the left of my min. Then I move to the right of my min. And I'm going to guess, so I get close to it. I press enter. And it gives me this for my value. We'll interpret them in just a second. And then we need to find our max, so we go second, calculate. This time, choice number 4 for maximum. Once again, we need to get to the left, so we're going to press our left arrow a bunch of times. Okay, I'm finally to the left, and it says move to the right, so I move over to the right. There we go. And then I move back and guess, hit enter. And we get our max and our min. So one thing we do want to take note of, when my calculator gives me this e to the negative 7th stuff, what does that mean? Yeah. Yeah, perfect. So this is scientific notation. And so it means times 10 to the negative 7th. So what that really means is I'd have to move my decimal to the left 7 places. So in other words, I would get 6 leading zeros, and then 6, 1, 5, 3. So if I had the number 0.0000006, that number is pretty darn close to just 0, right? So when we have something like that, it's usually what's called a numerical artifact, and you'll want to just round it to 0 when you have that scientific notation, because that's just an artifact of how our calculator calculates these things. All right. So let's take a look at our next example. So example 5 says, use the graph to write a formula for a polynomial of the least degree for this picture. All right, so the key idea that we're going to need is we're going to use the zeros to find the factors of f of x. Because remember, if we have a factor of the form x minus a, it's going to have a 0 of x equals a. So remember that zeros and x-intercepts are the same thing. So to find our x-intercepts, we would factor this polynomial. So we want to look at each of our zeros. So I have a 0 here, and my 0 is x equals negative 3. I have a 0 here, which is x equals to 0. I have another 0 here, which is x equals to negative, or x equals 4. So those are my zeros, but then I have some different behavior. So notice it says, use the graph to write a formula for the polynomial of the least degree. Well, that's important. So if we go back to the very beginning, when we were talking about zeros, we had two possibilities. If the multiplicity of a 0 is even, what does our graph do? Bounces. If the multiplicity of our 0 is odd, it's going to pass through. So then we look at our first 0. So if we have our 0 of x equals -3, does our graph pass through or does it bounce? It bounces. So that means it has to have an even degree. So what is the smallest positive even whole number? That would be 2. So our factor is going to be x minus a -3, and it's going to have the second power because it bounces. So we get x plus 3 squared. Now we're going to look at our next one. We have x equals 0, and it passes through. So that's an odd degree. So our factor is going to be x minus 0. And what's the smallest positive odd number? 1. So that's just going to simplify down to x. Our last one is at x equals 4. So once again, it bounces. So this is going to be even degree. So we're going to have x minus 4, and our smallest positive even number is 2. So our factor is x minus 4. And then we have f of x is equal to all of these factors. So we're going to have x minus 4 squared times x plus 3 squared times x. So there's also going to be a constant out in front. So if we were given another piece of information, we could determine that constant. In this case, that's the most general answer we were given. But if we were also told, for example, that f of 1 had to be 4.5, we could then use that to solve for a. So we would have 4.5 is equal to a, which we don't know, 4.5 minus 4 squared. Oops, I missed the first x. So it would just be 4.5 times 4.5 minus 4 squared times 4.5 plus 3 squared. So if we multiply all that out on our calculator, we would have 4.5 times 4.5 minus 4 squared times 4.5 plus 3 squared. That's going to give us 4.5 is equal to 63.2815 times a, and then we could divide by 63.2815 divided by 63.28125. So we take our 4.5, sorry, not 4.5. I did this wrong. I'm sorry. Let's back up and do this again. I grabbed the wrong number. So let's try this correctly. What's my input? What should it have been? This is my input. This is my output. So it should have been 4.5 equals a times 1 minus 4 squared times 1 plus 3 squared. I was like, that was looking really, really ugly. So 4.5 is equal to 1 minus 4 is -3. -3 squared is 9. So times 9. And 1 plus 3 is 4. 4 squared is 16. So 4.5 is equal to 1 times 9 times 16 is 144. So we divide by 144, divide by 144. So now we get 4.5 divided by 144. And let's get that as a fraction. We get 1 over 32. So then that would give us f of x equals 1 over 32 times x minus 4 squared times x plus 3 squared. And then if we were to draw a graph, let's go ahead and do that. So 1 over 32 times x minus 4 squared times x plus 3 squared. I'm going to have to change my window back to normal or to maybe 6s. So let's go window. Let's go negative 6 and 6. Negative, I'll leave that at 1. Negative 6 and 6. And now when we graph, we indeed see that our picture goes just off the top of our graph, comes down, hits our zeros. We get a picture that matches what we were given. So we can use the graph to reverse engineer a function that will satisfy what we're looking for. All right.